Yeah, so but remember all graphs are paper 1 except for trig graphs. Those are the only paper 2 ones, yeah. Sorry guys, I'm just looking for this one note from previous years that was quite nice, but it doesn't look like it's in here. I'm gonna have to do it from memory. Yeah. Yeah. Okay, it's fine. All right, guys, the standard form of this type of graph. We'll just write it down. Now, since it's a cubic graph, obviously we're going to have an x cubed. So it is going to be y equals ax cubed plus bx squared plus cx plus d. And it can be missing some of those terms, but if the highest exponent of x is 3, then it will be a cubic graph. So if it's missing the first term, then obviously it's not a cubic graph, right? Then it's just a parabola. Okay, but it can miss any of the others. Okay, now the a value is going to indicate the shape of the graph, as it does with all other graphs as well. So if your a value is positive, then the graph is going to look like this. It's going to be increasing, basically, at the beginning. Or sometimes you get graphs that don't have like a big dip like that. It can actually just have like a flat kind of bit there in the middle. We'll do ones like that. But it's increasing first. All right, if your a value is positive. If your a value is negative, it's obviously going to be the other way around. So it will be decreasing first. So it can have that kind of shape. Or like on the other side where it has like a flat bit. Now guys, if I make x equal to 0 in this equation, what am I usually finding for a graph if I make x equal to 0? The y-intercept. And what will I get? If that's 0 and that's 0 and that's 0, then my y-intercept will be d. All right, so that's also something that you can just remember. Your D value will always be the y-intercept, and it will be of the form 0 and then whatever that value is there. To get your x-intercepts, what will you do? Make y equal to 0, same as with any other graph. So for your x-intercept, make y equal to 0. So you're going to have a cubic equation. Now guys, that means that you can get possibly up to 3 x-intercepts, right? Because if you're solving a cubic equation, you could get 3 different x values, right? If you're solving an x to the power of 3. So you could get 2 x-intercepts, 3 x-intercepts, you might get 2, you might only get 1, depending on the type of graph. All right. But this is then going to be solving a cubic equation. Now guys, important for a cubic graph is you need to find your turning points. Now, do we remember for a parabola, how do we find the turning point? We have that formula that says that x is equal to negative b over 2a, all right? Now, there is no formula like that for a cubic graph, but what we are going to do to find the turning point or turning points possibly of a cubic graph, you find the derivative of this whole thing and you make it equal to 0. Guys, the logic behind that is at a turning point, right, your gradient is 0. Right, does that make sense? And what is the gradient of a function always? The derivative. Okay, so I'm just going to write here, gradient is 0, yeah, at a turning point. Now guys, if we just think of the type of function that we have, if we have a cubic function, the derivative of the cubic function will be a quadratic function. All right, so we will possibly get 2 different turning points. So if we're looking at this type of graph, that will be one turning point there, and that will be the other. All right, sometimes you only get 1 turning point. If you're getting like x minus 2 equals 0, when you're solving this derivative equal to 0 thing, then your graph will look like this. All right, then we just do like a little flat part instead of just making it go through that point. Be with you now, Emma? So we just make a little flat point just to show that there are technically 2 turning points on 1 point. Yes. That is not mine. There you go. All right, guys, now, morning. If we're looking at this type of graph, kind of halfway between the 2 turning points, we are going to have a point of inflection. I don't know if you discussed that last year with Mrs. Race in AP. The point of inflection is where your graph changes from being concave down to being concave up. So it changes its concavity. Now guys, concave down is like this part here, where it's almost like, I don't really know how to explain that. I've always been bad at that explanation, but it's kind of facing down in a way. So we call that part concave down, and then that part will be concave up. The point where it changes its concavity is called the point of inflection. All right, so we will do some examples on that, but let's just write it down. Point of inflection. Now to get that point, you're going to take the second derivative and make that equal to 0, and then solve for x. Or if your graph is in the other direction, the point of inflection will be where it's going from concave up to concave down. Mm-hmm. That's just a notation, so that's what we did in AP as well. It's the second derivative, so d squared in terms of x, sorry, x squared. Where the graph changes Concavity. Now, guys, the point of inflection, you don't actually have to show on your graph unless they explicitly ask for it. The turning point you do have to indicate. So we need to indicate all intercepts with the axes, obviously, like with any other graph, and then the turning points as well, all right, or turning point. Now, guys, in the case where you have two turning points, or sorry, where you have one turning point in this type of graph, the turning point is actually also going to be the point of inflection if it looks like this. Okay, so we are going to do examples, but let's just add that. So turning point is also point of inflection. Because if we just look at this graph, I know it's a very rough sketch of it, but does it make sense that for this part, it would be concave down, and then you have your turning point, which is your point of inflection, and on the other side of it, it's concave up. All right. So for this graph, this is a very specific one. This is where you're only getting one turning point, and that one turning point is then also the point of inflection. Yes. It's not the same type of concept. So yeah, let's wait until we actually do an example, and then we can discuss that again. All right. Okay, I think I've covered everything now. They can obviously ask you the normal questions like the domain and the range and so on. For the domain, it will always be x element of real numbers. And what do we think about the range? Also, y element of real. Hey, so these ones are quite nice if they ask you for domain of range. And it is y element of real because it's going down to negative infinity and it's going up to positive infinity. Right. I think I've said everything. All right. If I've left anything out, we can come back and add it. Let's do some examples. So we're just drawing today, but we are going to possibly answer some questions as well. Let me just get this. Okay, you can write examples so long, guys. I'm just going to leave open like 3 lines in case I remember something later and I want to come back and add it. Okay, no, it's not. Sorry. Oh, guys, I forgot to say, when you are solving for x here with your x-intercept, you are not allowed technically to use your silver calculator. All right, you can use it. I think I showed you the other day. You can find your 3x values, but then you need to actually show the one bracket and then your trinomial bracket and then your factorizing again. You actually get marks for that in cool. In AP, if you were to draw one of these graphs, you don't have to show the actual factorizing. You can just write the equation and then write your 3x values.
Yeah. It's sufficient to just have a bracket and the trinomial.
Yes.
Is that sure?
Well, you would have to show the bracket, the trinomial, and then the 3 brackets after that.
Yeah.
Yeah. Yes, but that is what you need to show. Yeah. Yeah. It depends on the question because they can ask it as separate questions or they can just ask you to draw the graph. So if they're asking it as separate questions, then you would have to show all those steps. Yeah, it just depends on the on the type of question. Oh, guys, this is a nice diagram. Let me actually just show you this quickly. So here they're just talking about the derivatives and the shape of a curve. Now, guys, we know that when your gradient is positive, right, that will give you an increasing graph, right? So if we're thinking of a straight line, if you have a positive gradient, it's an increasing line. Now, what they're showing here is that if you were to draw tangents at every point on this section of the curve, the gradient of all of those tangents would be positive, right? Because it is an increasing curve on this side of the turning point. So what they're showing here is that on this side, your derivative would be positive. So they can ask you, where is the graph increasing? Then you need to actually calculate where the gradient is positive. All right, we can write that down. At the turning point, what happens to the gradient? It is 0. On this side, now we can see that it's decreasing. So at every point on this part, right, you would have a negative gradient, a negative derivative. At the turning point again, the derivative is 0. And then there again, it's increasing. So the gradient would be positive. So there's something we can add to our note. So increasing where dy over dx is positive, and decreasing is where dy over dx is negative. So basically where the gradient is positive or where the gradient is negative. Then guys, we will look at it again in more detail when we actually have examples. They can also ask you where is your function concave up? And that will be where the second derivative is positive. And where is it concave down? And that will be where the second derivative is negative. It's a bit difficult to explain that without a graph, so we can chat about it when we have an actual graph to look at. But that's quite easy to remember, guys. Up is positive, down is negative, right? Yeah. Mhm. Yes. Yeah.
Now, the gradient goes from decreasing in value to increasing.
So where it goes from decreasing to increasing. No, well, if you look at this, your point of inflection will be here somewhere,
Yeah.
but the gradient is still decreasing.
As in, the rate, the rate, as in it's getting smaller, 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 and it starts getting.
Yeah, okay, so the concavity has to do with the derivative of the gradient. Yes, so it is true what you're saying. Yeah, but let's just do an actual graph and then you can look at specific values. Right, but yes. Okay, guys, let's draw one. Let me just find a nice equation here that's not too complicated. Okay. Examples, number 1. Draw the graph of f of x Okay, guys, now we're going to have to calculate all of the stuff that we've written up there, basically up until the end of turning points. We are going to find the point of inflection as well, just so that we can discuss it. But in the question, they haven't specifically asked for it. All right, so in the test or exam, if they don't say anything about a point of inflection in the question, don't calculate it. You're going to waste your time. So the first thing that we need to notice is that our A value is positive. Right, now that is just telling us what the shape is going to look like. So that's almost like a bit of a test. Once we've plotted all our points, we know that it should be increasing first, right? Because A is positive. What is the y-intercept? -4, so we can write that down. The y-intercept is going to be 0, -4. Now we can find our x-intercepts. So we're going to make the whole thing equal to 0. Guys, I'm assuming that you will all just use your calculator for this. Am I right making the correct assumption? So let's quickly just look again at how you can do that without the marker noticing. So you go to equation and you go to the fourth one, which is the cubic one. Oh, sorry, I don't know what I did there. Then you type in your A value, which is 1, you press equals. Your B value, which is -6. Your C value, which is 9, and your D value, which is -4. Then you press equals, and then it gives you one bracket. Now, guys, if your X value is 4, what is that bracket going to be? X minus 4. Now from here, you can do that multiplication method to get the trinomial bracket, or you can just use the calculator, but let's go over that method quickly. You look at what you need to multiply this bracket by to get the cubic equation. So what does I multiply x by to get x cubed? X squared. All right, for our last term, I'm not going to write that in yet because I'm not sure about spacing, but what is it going to be? What must I multiply -4 by to get -4? 1, so it's going to be +1. Okay, that's going to be my last term. But let's quickly check for the middle term. If I multiply these two, I'm going to get -4x squared. What must my x squared term be? -6. So I need to do -2x because that is what I'm going to get when I multiply those terms together. X times -2x is going to give me -2x squared. So then I have -4x squared minus 2x squared, which is -6x squared. And then we do our +1 equal to 0. Now, guys, from here, you can either just factorize this trinomial or you can use the calculator. If I factorize it, what am I going to get? X minus 1 and x minus 1, hey? So we're going to have x minus 4. You can write them as two separate brackets if you want, or as x minus 1 squared. It really doesn't matter. But if we had used the calculator, they would obviously just give us one other answer here. X equals 1. All right. And then, yeah, we're going to have to figure out which one is double, I suppose. Okay, so how many x-intercepts am I getting here? So x equals 4, or x is equal to 1. So my x-intercepts are 4, 0, and 1, 0. Okay, so we have y-intercept, we have two x-intercepts. We still need to find our turning points. And for that, we do the derivative equal to 0. Sorry. Now, because we've written it as f of x, we can write f dash x. So f dash x must equal 0. So the derivative of x cubed is 3x squared. The derivative of minus 6x squared is minus 12x. And then plus 9 equals 0. Then I'm just going to divide through by 3. Is that fine with everyone? So x squared minus 4x plus 3. So what are my brackets going to be here? -1 and -3. So x minus 1, x minus 3. So I'm getting two x values here for my turning points, x equal 1 or x equal 3. Now guys, these are the x values of the turning points. How am I going to find the y values? Sub them back into the original equation. Now guys, I just want to bring your attention to this. X equals 1. We already have a point where x is equal to 1 here. Can I have a different point where x is equal to 1 on one graph? No. All right. So we don't actually have to sub this x value back into that equation. We know already that we're going to get 0. All right. So from here, I'm going to get 1, 0. And quickly, if we sub in x equals 3, -4. All right. What I want you to notice is that we have a turning point that is actually also one of our x-intercepts. And do we notice that it is the turning point that appeared in two brackets? All right, so that's almost like a double turning point. Sorry, a double x-intercept, I mean. A double x-intercept is actually also our turning point. All right, so that's something that you, yeah. You must just notice, I suppose. So where shall I write that? We've underlined here. I'm just going to write double. I'm just going to put that in quotation marks. That's not really a proper term. Yes. Yes. Okay, draw this graph, please. You have all the information that you need. Can anyone see my remote? Is it somewhere here? Thank you, the white one. Thanks so much. It has to be like kind of a round curve, not like a, yeah, it mustn't be, it must be rounded kind of out, yeah, on the outside. So guys, this part is supposed to be concave down and that part is supposed to be concave up, if that helps. All right, so kind of rounded outwards. I suppose mine is also almost looking a bit, but yeah, they're not very strict on that. As long as they can see that you have attempted to make it like a round curve in a sense. I can show you what the one in the book looks like. They space their x-axis out a bit more, so it looks better than mine. So it looks like that. Right? Does that make more sense? Okay. Now guys, these two turning points, they actually have specific names. The one is called a local minimum turning point and the other one is called a local maximum turning point. I'm sure we know which one is which. Don't know if you discussed that last year. Oh gosh. A warm up.
She'd do it with us, and then she'd finish twice, and then she'd be like,
Okay, I see. All right, guys, the local maximum turning point is obviously the one that is the higher one than the other one, the local minimum. And guys, it's called a local max and a local min because it's not actually the maximum point on this graph, right? If we look at the other side there, the graph does continue going up, but this is like a point of interest in the sense that the gradient actually changes from being positive, now it's 0, and then on the other side it's negative, the gradient, right? In terms of it's increasing, there it's 0. Oh, we also call it a stationary point, by the way, turning point, stationary point, it's the same thing. And then it's decreasing on the other side. Then the one of the two turning points that is lower is called the local minimum turning point. Again, local because it's not actually the lowest point on the graph. It's not actually the minimum value, but it is, yeah, the lowest one that we can calculate in a sense. Okay, now guys, the point of inflection for this one, I do actually think we probably need to spend some time discussing second derivatives in AP as well. So we will chat about this stuff a bit more tomorrow. I also have quite a nice note from the Mind Action series that I actually want to copy for you guys. But let's quickly work it out. I'm going to do it in pink because this is like the extra one that you don't actually have to do unless they ask you for it. At the point of inflection, that is where your second derivative is equal to 0. So now we know, obviously, your second derivative is the derivative of the first derivative. Now, guys, remember that this was our first derivative, not the simplified one, not the one where we divided through by 3. All right, this is our first derivative. So we have to derive that one. Okay, we simplified it so that we could solve for x, but that is the first derivative. So it is 6x minus 12 equal to 0. So 6x will be equal to 12. So x will be equal to 2. Yes.
Is the point of inflection always halfway between the both?
Yes, it will be. The point of inflection will always be halfway between your one turning point and the other turning point, but they do want to see this working, all right, because that's where the concept comes from. But if they're just asking you to draw the graph and they just say, plot the point of inflection, then you can just do that, all right? But if they're asking it as a separate question, then you will have to show this. So the point of inflection, guys, that is our X value. What is the Y value? How am I going to find it? By subbing it in. Can someone do that quickly? -2. All right, so 2, -2 is our point of inflection. Guys, remember we're subbing it into the original function, not back into the second derivative or the first derivative or whatever. All right, so 2, -2, that will be our point of inflection. Yeah, I think it's pure luck that mine does, but it's fine, it doesn't really matter. So guys, on the left of this point, the graph is supposed to be concave down. On the right of that point, the graph is supposed to be concave up. But in a test or exam, we're not actually going to check that. We're not going to say, okay, the point of inflection is here. So is this graph concave down? Is it concave up there? If not, -1 for shape. We're not going to do that. Okay, just try and make your shape kind of as round as possible in a sense. Okay, guys, we will discuss this in more detail tomorrow, how the first derivative and the second derivative actually influences things and the different types of theoretical questions that they can ask you. For now, I just want to give you some time in class to actually practice drawing these. I don't think they're too difficult. It's just calculating points and plotting them. Oh, we didn't actually do an example now. Can I just show you this example quickly? We don't really, I don't want to use the next 20 minutes just on drawing another graph. In the textbook, they have example 2. All right, they've written it in this form, but that is a cube there. All right, so this is a cubic graph. For A, they're saying determine all stationary points of F. Now, the stationary points are the turning points. All right, and use the first derivative test to decide on the nature of the stationary point. Don't worry, we'll talk about that tomorrow as well. That all goes along with there's a first derivative test and a second derivative test. We will discuss that tomorrow. Basically, find the turning points. That's what you need to do for A. B, find the intercepts with the axes, and then C, draw the graph. All right, so for the stationary points, what are we going to do for, what are we doing here? Oh, they multiplied it out, sorry, obviously. All right, so you would have to multiply it out before you find the derivative. Remember in core, that's what we do when we derive stuff. We need separate terms. Then you make the derivative equal to 0, and you solve for x. All right, so here they're only getting one x value when they're finding the stationary point. So this is a type of graph that only has one turning point. Then they're subbing it into the function, they're getting 8 as the y value. So hence -1, 8 is the only stationary point of f, right? We're getting one turning point. Then they're doing the test. Don't worry, we'll do that tomorrow. We'll write a little note on it. They're finding the x-intercept here. The x-intercept is also 1. What did we get here? -1. Sorry, the x-intercept is 1. Yes.
Isn't this pretty similar to the turning point form of the graphic graph?
What do you mean?
Was it a bracket x minus 2 plus q?
Oh, yes, I see what you mean, the way that it's written.
And the
Yeah, I didn't notice that. Yes. I wonder if you would. I'll look into that. I actually have never noticed that before. Yeah, but it does look like it. And it should be because that thing is then equal to, okay, I'll think about that a bit, but yes, it does look like it. All right, so we're getting an x-intercept of 1 and a y-intercept of 7. How would we get the y-intercept if it's written in this form? I know we've multiplied it out. We can see that it's 7 there. But if we were doing the y-intercept first, for example, this isn't written in that standard form. So you can't just say, okay, 8 is going to be your y-intercept. You would have to just make x 0, right? So if it's not written in that form, just make x equal to 0 and solve for y. That will give you a y-intercept. Now I just want you guys to look at the shape of this graph. All right. Also, another thing is our a value here and there is negative. So it has to be decreasing first. But because we're only getting one turning point, guys, it's one of these graphs where you have like a flat section in the middle there. And in this case, actually, when you have that, your turning point is also your point of inflection. Right? So you wouldn't even have to calculate the point of inflection. In this case, you can just look at it and you can see that there we have a concave up graph, and there our graph is concave down. I shouldn't say graph, I should say section. The section is concave up, and that section is concave down. Now, guys, this is what Georgia was asking, I think, is in this case, you would actually have to calculate the point on this side of your turning point. All right, I know they didn't do it in the textbook, but for exam purposes, you do, because what do we actually have? We only have our point of inflection, turning point, the same thing here. We have our y-intercept and we have our x-intercept. We have no information on this part, this half of the graph. All right, so you would have to see that your turning point is at x equals -1. Then you would have to sub in x equals -2, for example, just to get that shape. Yes. You could use symmetry, yes, that would also work. But what I'm saying is you do need some information on the other side of the turning point as well. All right, either subbing in or using symmetry. Okay, you are going to do exercise 9.1. Let me just see which ones I want you to do. This is on page 216. Oh, sorry, page 216. So guys, here they again saying, use the first derivative test. Don't worry about that. Don't worry about these doing like an ABC. You're basically just going to draw the graph. All right, like we did in the example. So let's see. I want you to do number 4. Now guys, how are you going to factorize number 4 if you're making y equal to 0 and solving for x? You're going to take out x as a common factor, hey? X, there we go. And then you're going to have your trinomial. Number 5, I want you to do. In this one now, you can't just take out x as a common factor because there is no x in your last term. And then I also want you to do number 7. Okay, 4, 5, and 7. And as you can see, after this, we're going to talk about concavity, points of inflection in great detail. Right? I just want to put together some comprehensive note on that before we jump in. Okay, get going, guys. Yes. Yeah. No, it's not in. Yeah, it's because of chain rule essentially. So it only makes sense to me if I write it with intercepts instead of a y. No, there's no trick. If I just look in the textbook, they probably doing like maybe at university, but I never did it at varsity. No, I'm sure I've never seen that before, not even at university level. Yeah, but in other countries they do more complicated stuff than we do, unfortunately. Yeah, when I went to America on an exchange program and they were grade 9s doing this work. Yeah, made me feel a bit bad about myself, but anyway. I'm just checking here just to make sure. No trick. No, don't worry about that.